Now let's try to apply KVL on this diagram. The first step is to mention all the branch voltages in a given loop along with their polarity. Just like in KCL, where we assumed directions of unknown currents in the beginning, here we will have to assume polarities of all the unknown voltages. So let's say that we come up with these assumptions for the voltages. So for all the vertical components x1, 3, 5, and 6, I have assumed their positive terminals to be the upper one and the lower terminals are taken as negative. And for the horizontal components, let's assume their right terminals are negative and the left terminals are positive. So let's go with this assumption. And now we need to write the KVL equation for each of the loops. This is the first loop, second loop, third loop, and then we can combine the pairs of adjacent loops. So this would be the fourth loop, this could be the fifth loop, and then if we combine all three, then this would be the sixth loop. So overall we have 6 loops, and let's first write down the loops. So first one is x1, x2, and x3. x1, x2, x3. This is our first loop. The second loop is x3, x4, x5. The third loop is x5, x6. x5, x6. And now let's combine the first and second loop to make the fourth loop, x1, x2, x4, and x5. Similarly, if we combine first, second, and third loop, x1, x2, x4, and x6, x1, x2, x4, x6. This is our fifth loop. And for the last one, we can combine this second and third loop, so that becomes x3, x4, x6. x3, x4, x6. So that is just how I am writing the loops. You may write them in a different sequence, but overall there are a total of 6 loops. Now for each of the loops, we need to write the voltage rises on one side and the voltage drops on the other side. Let's assume that we are going to go in the clockwise direction for all these loops, okay? Now it's totally your choice, but let's assume this clockwise direction and let's write down the equations. So for x1, if we go in the clockwise direction, here we go from negative terminal to positive terminal, which is a voltage rise. Then for V2, it turns out to be from positive to negative, which is a voltage drop. Similarly for V3, we go from positive to negative, which is a voltage drop. So there is one voltage rise, which is V1. We write it on one side. The other twos are voltage drops. So V2 and V3 are voltage drops. We write them here on the other side, V2 plus V3, which is the sum of voltage drops in this loop. For the second loop, again, we go in the clockwise direction. So V3 turns out to be voltage rise. V4 and V5 turn out to be voltage drop. So V3 goes on one side. That is equal to the 2 voltage drops added together, V4 and V5. V4 plus V5. Then for the last one, again going in the same direction, V5 is from negative to positive, which is voltage rise. And there is another voltage which is from positive to negative in clockwise direction, and that is a voltage drop. So V6 on the other side. Now for x1, x2, x4, and x5, 1, 2, 4, and 5, if we again go in the in the clockwise direction, we see x1 as V1 as voltage rise. V2, V4, and V5 are all voltage drops, so they will be added together. V2, V4, and V5. V2 plus V4 plus V5. For x1, 2, 4, and 6, which is the biggest loop, again we have only one voltage rise, V1, and voltage drops are 2, 4, and 6. V1 equals to V2 plus V4 plus V6. And lastly, for V3, V4, and V6, V3 is a voltage rise, V3 is a voltage rise, and V4 and V6 are voltage drops. X3, X4, and X6. Yes, we have 2 voltage drops and 1 voltage rise. So these 6 equations are all when we go in the clockwise direction, clockwise and clockwise. Now the question is, what happens if we go in the anti-clockwise direction? How are these equations going to change? Well, going in the opposite direction, of course, the voltage rises will appear as voltage drop and vice versa. So let's look at the first loop going in the counterclockwise direction this way. So let's cross out the first direction and let's go in the counterclockwise direction. So see what happens to equation, and we will only look at the first loop and we can extend that concept for all the other loops. So this time you see we go from negative to positive for V3. So it appears as a voltage rise. Similarly, V2, we go from negative to positive. So again, it is a voltage rise. But V1 here, now we go from positive to negative, which is a voltage drop. So voltage rises first, V2 plus V3, V2 plus V3, that is the sum of voltage rises, is equal to the sum of voltage drops. There is only one voltage drop, which is V1. So that would be the new equation for the first loop. And if we compare this one with the original equation, you see both equations are exactly the same. The only difference is the previously left-hand side has now become the right-hand side, and the previous right-hand side has now become the new left-hand side. That is the only difference, but overall the equation is exactly the same. So again, going either in the clockwise or counterclockwise direction to cover the loop does not make any difference. Of course, as long as the same direction is followed throughout the loop. Now, since voltage is a directional quantity, we need to find both the magnitude and polarity for each unknown voltage. Just like KCL, in KVL we assume polarity of unknown voltages and then use KVL to find the unknown voltage. And as a result of our calculations, a positive voltage means our assumed polarity was correct, and a negative result means that the actual polarity is opposite to what we had assumed. And to rectify that, we would reverse its assumed polarity. And to illustrate that, let's look at the same situation once more, and let's write down the equation for loop 1, which is V1 equals to V2 plus V3. Now let's say that we know two of these voltages. The first one, let's say we know this to be plus 9 volt, and this one, let's say we know this to be 6 volt. And we want to find out the V2. So as per the equation, V2 equals to V1 minus V3. And if we put these values, V1 equals to 9 volt minus V3 equals to 6 volt. So it turns out to be 9 volt minus 6 volt is 3 volt. Now, as a result of our calculations, this unknown voltage, its value turns out to be positive, which means that our originally assumed polarity for V2 is correct, and we can simply write it down as V2 equals to 3 volt. On the other hand, let's assume that now V1, we know this as 4 volts and V3 as 6 volt. So with these values, if we try to find out V2, V1 here is 4 volts. So let's put in the value minus V3, which is 6 volt. So this one in this case turns out to be minus 2 volt. So if such a situation occurs where as a result of your KVL calculation, the unknown voltage value turns out to be negative, well, in that case, what you're going to do is you are either going to write this V2 as minus 2 volt with the originally assumed polarity, or a more preferable way would be to reverse this polarity. The originally assumed polarity was positive here, but if we reverse it, the positive would be the other terminal and the negative terminal. The positive becomes negative, the negative becomes positive, and with this reverse polarity, now we can write V2 as 2 volt. So again, if you do the calculations of KVL and the unknown voltage turns out to be positive, that means your originally assumed voltage polarity was correct. On the other hand, if your result turns out to be negative, that means you need to reverse the originally assumed polarity of that voltage, and you need to make the sign of your calculation positive. So that is how you solve KVL equations and interpret their results. So I hope this makes sense, and thanks for watching. I will see you in the next lesson.